Hello there guys, Teacher Krishna here and welcome to our next class for the third unit. This is a class that is part of Beehive School and 10th High School. Our subject is Physics 1 and we're working on week number 26 today. So be welcomed and let's go over our presentation. Remember to have your notebook with you in order to make today's summary. Just like every week, you need to include the date, the ending line, the title, the summary itself, and finally some additional decoration. Here you have our ending line for today. Number and describe fundamental forces that are constantly applied to objects in the universe, as well as create models that pretend to replicate the representations of such forces. This is a pretty interesting topic once you analyze it, so I'm pretty sure that you're going to find it very enriching. Here you have a summary of the activities that you need to complete. So first of all, watch this video and make a summary. You need to read topic 3.04 and complement your summary. Complete the questions from 5 to 9 from page number 3. And lastly, once you are done with all of these activities, you have to go to topic 3.04 and take the quiz online. Alright? So let's go over our topic, and today we're going to study fundamental forces. So scientists have discovered that there are 4 elemental forces that act on matter. We have gravity, electromagnetism, strong nuclear forces, and weak nuclear forces. So what's very interesting about this topic is that you are going to find some of these forces on a daily basis. For example, if we analyze gravity in electromagnetism, you are going to find out that gravity is absolutely everywhere, not only talking about the gravity that is produced by Earth, but gravity is found in every single object that has mass. So your body has gravity, your cell phone has a gravity as well. And when we talk about electromagnetism, we are going to, of course, have to learn about some electromagnetic fields that are going to act upon different objects without the necessity of touching each other. And of course, the strong nuclear forces and weak nuclear forces are very interesting as well, with some examples that I will show you later on. So let's start with some theory with strong nuclear forces. They are forces that keep the nucleus of the atoms together, and it is the strongest force of the 4 that were mentioned. So just like you know already, we have several elements in the natural world. For example, we have hydrogen, we have helium, we have carbon, oxygen, iron, so on and so forth. We have many elements in the natural world. But remember that in the nucleus of each one of the atoms, there are protons as well as neutrons. And the force that actually keeps it together are the strong nuclear forces. Okay? And now let's go with electromagnetism. They are, negative charges, they attract positive charges. This principle can be exemplified if you have 2 magnets, one with a positive charge and one with a negative charge. So what happens if you put them close to each other? At the end, they are going to attract themselves and they are going to end up touching each other. Okay? And electromagnetism is the second strongest force out of the 4 that we are studying here. Then we have weak nuclear forces. Forces produced by radioactive isotopes. It happens when the nucleus of an unstable atom separates into pieces. So actually the strong nuclear forces and the weak nuclear forces are strongly related somehow. Because sometimes when a strong nuclear force is disturbed, then it is going to generate weak nuclear forces when generating unstable isotopes or unstable atoms that are going to start separating. And lastly, we have gravity. It is the weakest of all the forces. It is a force that attracts objects to one another. The bigger the objects, the bigger the gravitational pull. And the farther away, the weaker it gets. So let's suppose that you're traveling to space and you find yourself just floating in the outer layers of the atmosphere without a disruption of the gravitational pull of Earth. So at that point, what's going to happen is that your body is going to generate what we know as microgravity. And basically, your body is going to start attracting other objects with a lower mass. Let's suppose that you have some water, for example, and you put the water close to your body, then you will notice that it will attach somehow because of the microgravity that both of the matter that you are taking into account are generating. Okay, and right over here we have a small summary of the four elemental forces that you find in nature. So we have electromagnetism, we have a weak interaction or weak nuclear forces, we have a strong interaction or strong nuclear forces, and lastly we have gravitation or gravity. And in order to remember them better, I suggest that you can make some simple drawings in your notebook so you can re-study them later on. Alright, so how do we relate all of this theory to Albert Einstein and of course to atomic bombs? So pretty much what happens was that Albert Einstein was studying nuclear forces, and of course he is one of the people that actually contributed in the creation of atomic bombs. So he noticed that after analyzing these forces, specifically the strong nuclear forces and the weak nuclear forces, a gigantic amounts of energy can be released through a process that is known as fusion. So fusion is basically the a process that's taking place in our sun. So there are several atoms that are combining among each other. So hydrogen, after it combines with more hydrogen atoms, it changes into helium. Then after a lot of helium atoms combined with hydrogen atoms or with other helium atoms, they are changed into lithium, so on and so forth. So the recombination of all of those materials and elements, it causes gigantic amounts of energy. That's why we can actually look at all of the stars and of course at our sun shining every single day, and the stars can live up to billions of years. So Albert Einstein was studying how to produce such reactions. So basically he noticed that if actually humans are capable of actually building a new element through the fusion of several atoms and combining them into a new element, so specifically talking about the particles in the nucleus of the atoms, what's going to happen is that that gigantic amount of energy is going to be released, and of course it will be translated to our eyes as an atomic explosion. And Albert Einstein also discovered that let's say the less amount of components that an atom has in the nucleus, the stronger the explosion will be. So far, the deadliest weapon that humans have created has been the hydrogen atomic bomb. So pretty much they are going to disrupt the of course nucleus of the hydrogen through fusion and through fission as well, with the use of other components such as uranium, which is a very unstable element that humans use to disrupt the nucleus of several atoms. And of course they can be translated into a gigantic explosion, just like the ones that we have seen through history. And that's basically how it is related to the real world. So now let's go with universal gravitation, and of course in the Coulomb's law. You are going to find that both of them have the same formula, but there is one constant that change. So in pretty much in the Coulomb's law and the universal gravitation, what is going to be explained is that in some cases the charges are going to be attracted to each other, just like in this case, positive and negative, and in some other cases they are going to repel, just like when you have the same charge, in this case will be positive and positive. But if you put two magnets that have a negative charge, they are going to repel as well. And of course, we have to talk about field forces, the magnetic field that surrounds a magnetically charged object, and they can push or pull other atoms without touching. So, for example, in this case, imagine that the circles that you see here are magnets. And of course, what your eyes will actually see will be only the circles that you have right here. But in reality, there is more to them. So basically, there is going to be a magnetic field that is going to surround them. And just in case you just place them a little close to each other, you will notice that they are going to attach immediately if they have opposite charges. So that's caused because of the field forces. They can attract objects without the necessity of touching each other. Okay. So I copied this directly from Agilex, so you could actually take a look at the general variables, of course, representation of the formulas, because I cannot really type it down in a PowerPoint presentation, so it's better if you directly see it from the way it is presented in there. So let's start with the Newton's law of universal gravitation. And it states the following sentence. Every mass in the universe attracts every other mass. Just like I was telling you, if you go to space and you have water close to your body, then of course your body is going to attract the water, and the water is going to attract your body when creating a microgravity. And so let's continue. In the universe, with a force that is directly proportional to the product of the two masses involved. So remember that when we say that it is directly proportional, that means that if one value increases, the other one will do as well. So translating it to simpler words, it will be that if the mass of the objects that you are taking into consideration are larger, so will the gravitational pull will be. The same thing will happen in the other way around. So if you have two objects with a very little mass, the gravitational pull among both objects is going to be very little as well. And let's analyze the last part, and it's inversely proportional to the square of the distance separating them. So the farther away both objects are placed from each other, the smaller the gravitational pull will be. So a littler distance will be translated into a higher gravitational pull. And a higher distance will be translated into a smaller gravitational pull. That is why it is inversely proportional. While one of the values increases, the other one is going to decrease. So let's go over the formula that we have for this specific universal law. So the equation for Newton's law of universal gravitation is the following. So right over here, you're going to have all of the components. So I suggest that you copy this formula in your notebook, as well as what each one of these values stand for. So first of all, we have Fg. That equals the gravitational force between the two masses, measured in newtons. That is very important. Your result is going to be in newtons. Alright, let's continue with letter G. And something important that you have to remember is that scientists have tested this specific value through history. So basically, if it was first measured by Henry Cavendish, and scientists noticed that it is going to be a constant. So no matter what problem you are applying, or what problem you are trying to solve, this value is going to remain constant. Okay, so if you can try to memorize this value, will be the best thing that you can do. So G will equal 6.67 E minus 11 newtons meters square per kilograms square. And something that I have noticed is that students kind of confuse the E minus 11. So in this case, of course, you can type down directly the letter E in your calculator, but that wouldn't be really accurate. We just have to remember a little bit the math notation. So, or the scientific notation, I'm sorry. So basically, what's going to happen right over here is that this E is standing for times 10. All right, so in this case will be a 6.67 times 10, and this one is going to be the power that we are going to elevate number 10 to. So it will be 10 elevated to the minus 11th power. All right. So please make sure to take that into consideration. Don't write E directly, but instead of the E, write times 10, and then elevate 10 to the power that we have next to the letter E. Anyways, we're going to have some application problems later on, so there you will have the chance of actually applying all of the formula and everything. But so far, take it into consideration. Let's continue with the values that we have right here. So we have M1, which is going to stand for the mass of the first object measured in kilograms. We have M2, which is the mass of the second object that is going to be measured as well in kilograms. And lastly, we have a D to the second power, which is the distance between the objects squared, measured in meters. Alright, so let's continue. And right over here we have another section that is for the Coulomb's law. And something that I want you to take into consideration is that the constant is going to change depending on the formula that you use. So if you're talking about the gravitational pull specifically, related to the Newton's law, the constant is going to be letter G. And in this case, if you're applying a problem that is part of the Coulomb's law, the constant is going to be letter K. And they are going to be a little bit different, but take it into consideration, please. So we're going to talk about the Coulomb's law of electrical forces, and it states the following. For charged particles that are smaller than the distance between them, the forces between two charges, I'm sorry, this part is kind of disrupting me a little bit right there. So we're going to continue with the next line. The product of the charges and inversely as the square of the separation distance. The force acts along a straight line from one charge to the other. So this is pretty similar to the Newton's law that we were analyzing before. But this time, instead of analyzing directly the mass of the objects, we are analyzing the charge of each one of the particles that we have right here. Like if we had two magnets, right? Like if we had a magnet 1 with a positive charge and magnet 2 with a negative charge. So right here we're going to measure like the attraction or the interaction that is going to be generated. But the same thing happens right over here. So the higher the charge that the particles have, the higher the attraction they will produce. And the farther they are away from each other, then the less they are going to attract themselves. Okay, and right over here you have the equation. The equation for Coulomb's law is Fe equals, in parentheses, K Q1 Q2 divided by D to the second power. Okay. So now we are going to take a look at what all of these letters stand for. We have Fe, which is the electrical force between the two charges measured in newtons. The representation of the result will be in newtons as well. And here is where the constant change. Remember that letter G is different than letter K. And right over here, letter K will equal 8.99 E9 newtons meters squared divided by Coulomb squared. Coulombs because we are analyzing the Coulomb's law. So these are coulombs, okay? We have Q1, the quantity of charge of one particle measured in coulombs. Q2, the quantity of charge of the second particle measured in coulombs. D squared, the distance between the objects squared measured in meters. And right here we have an observation. The unit of charge is called the coulomb, and it will be abbreviated as letter C. A charge of 1 coulomb, or 1C, is associated with 6.25 billion electrons. And this might seem like a great amount of electrons, but it only represents the amount of charge that passes through a common 100-watt light bulb in a little over a second. So that's astonishing because imagine we have 6.25 billion electrons. So imagine how tiny those particles actually are. And going back to the theory we were analyzing with Albert Einstein and of course the atomic bombs, imagine the destruction that can cause one atom when it changes, and of course depending on the reactions that are caused there. Alright, so now that we have the theory and everything, we're going to move to the application problems. So we're going to talk a little bit about everything. Well, let's start with problem number 1. So here is a sample of problem. The Earth and the Sun are 1.511 meters apart. Use Newton's law of universal gravitation to calculate the force of gravity between Earth, which has a mass of 6.0 e24 kilograms, and the Sun, which has a mass that equals 2.0 e30 kilograms. Alright, so remember that the first step is to write down the givens from the problem. So right over here we have the first mass, that will be the mass of Earth, that is specified here. We already have mass of the second object, which is going to be our Sun. We specify it here. We have the distance that separates them, which is specified here as well. And lastly, remember that G is a constant in the Newton's law. So you just have to copy it directly, not from the problem, but from the constant that we are usually going to use in such problems. So now that we have all of our information, we are going to write down our formula, and this is the formula that we are going to use in order to solve our problem. So we are going to substitute the values. Of course, we have letter G, which is 6.67 e minus 11, and of course we already have all of the units. We have mass number 1, which is going to be 6.0 e24. We have mass number 2. We have 2.0 e30 kilograms, and make sure to actually add everything in parentheses. All of this should be in parentheses. And we are going to divide all of that by the distance squared. The distance will be 1.5 e11 meters squared, of course. So like, I know that when you see all of these numbers it might seem complicated and everything, but in reality it is not. Like, I would suggest that you go by parts. Like, if you want, first you can multiply letter G by M1. When you have the result, you can multiply the result by M2. And when you have the result, you can divide all of that by D squared. But go by sections, because just like I always tell my students, sometimes what happens is that when you try to write absolutely everything in the calculator, you might get confused, or you might not actually get the correct result. So please make sure to do it by sections. And of course, remember one more time, letter E is not directly letter E in your calculator, but letter E is going to be substituted by multiplying this number times 10 and elevating number 10 to the power that you have right here. So one more time, in this case it will be 6.67 times 10 elevated to the minus 11th power, multiplied by 6 times 10 elevated to the 24th power, times 2 times 10 elevated to the 30th power. When you get your result, you are going to divide that by 1.5 times 10 elevated to the 11th power, and all of that elevated to the second power. Alright. And by the way, here, this should be your result. Your answer will be 3.6 e22 newtons. Remember that the answer should be placed in newtons. Alright, so look at the answer. Is the force the Earth exerts on the Sun, or is this the force that the Sun exerts on the Earth? So let's remember a little bit about the Newton's third law, and remember that whenever we are comparing the forces that are being applied over two objects, they are going to be exactly the same. So in this case, this is the force the force that Earth is exerting on the Sun. And of course, this one is going to be the force that the Sun is going to exert on Earth. And yeah, pretty much that's what they are explaining right over here. Like the application of the same forces but in opposite directions. Alright, now let's go with problem number 2. Jenny loves puffed rice cereal. As she is pouring the cereal, 2 little pieces of cereal, each with equal charges of 1.85 E minus 18 coulombs, fall into the bowl and 0.025 meters apart. Use Coulomb's law to find the electrostatic force between them. Alright, so first of all, you have to list the givens, just like always. So we already have the charge from the first particle that is specified right here, 1.85 E minus 18. Then we have the charge from, well, both of the particles that went down to the ground actually have the same charge. So we just copy the same. We already have the distance, since it mentions that they are apart by 0.025 meters. And lastly, letter K. Remember, letter K in the Coulomb's law is a constant. So it is not necessary that they specify it in the problem, but you can just write it down directly. Alright, here we have our formula. We are going to substitute it with our values. We have letter... Well, in this case, it should be... Well, hold up. I think I made a mistake right over here in the presentation. So, pretty much you have to substitute it with these values, but I have them different. So, I'm sorry guys, we are going to skip this problem. And if you want, we can go back to this problem during the live presentation, okay? I'm sorry about it. I didn't notice that I included different information. But let's go with problem number 3. And just make sure to remind me about this problem so we can go over it during the live session. And of course, we can take a look at how to apply everything, which is pretty simple anyways. So here we have Mrs. Young, an online school administrator, has a mass of 50.5 kilograms. Her computer has a mass of 2.3 kilograms. The separation between Mrs. Young and her computer is 0.75 meters. So how much gravitational force does Mrs. Young exert on her computer? And how much gravitational force does her computer exert on her? So, first of all, remember, you have to list the givens. We have the first mass, that is from the administrator. We have the second mass from the computer. We have our distance. And of course, we have the value for G. And of course, we are looking for the force that actually they are producing among each other. Alright, so now we are going to substitute the values right over here. So we have letter G. We have the value for the M1, the value for M2, divided by the distance squared. Once you operate everything by sections, you are going to get that the result is 1.38 E minus 8 newtons. Alright, or if you want to actually approximate it to only one decimal, you will have 1.4 E minus 8 newtons. And the magnitude of the force is the same as in part A. So just like I was telling you, remembering about the Newton's third law, actually the force that is going to be produced between the computer and the administrator are going to be exactly the same. Alright, and let's go with one last problem. A 2.5 kilogram rock is located on the Earth's surface. If the mass of the moon is 7.4 E22 kilograms, and the separation distance between the center of the rock and the center of the moon is 3.8 E8 meters, what gravitational force does the moon exert on the rock? So this is pretty interesting because we're still analyzing the gravitational pull between a simple rock and a very large object such as the moon. So, of course, let's list our components. So we have M1, the mass of the rock, 2.5 kilograms. We have M2, which is the mass of the moon, is 7.4 E22 kilograms. We have our distance of separation, which is 3.8 E8 meters. And of course, we have our constant, that is G, 6.67 E minus 11, and of course, the units of measurement. Remember that we are looking for the force. So let's go ahead and let's substitute all of the values inside the formula. We are going to substitute letter G. We substitute letter M1, letter M2. We multiply those three values, and then we are going to divide everything by the distance squared. So we are going to find out that the gravitational pull in this case will be of 8.55 E minus 5 newtons. Or one more time, if you want to approximate it, it will be 8.6. Alright guys, so I know it's a very long presentation for today. Half an hour, wow, that's probably the longest session that we have had so far. So probably it might seem complicated, but in reality it is not. Just follow the process for solving the problems that we have used before. List your givens, use your formula, operate it section by section, and you will be more than fine. So thank you guys for coming. Remember to go to the activities section so you can notice what other activities you have to complete besides the summary of today's session. And I will be seeing you around during the live meet that we have, no, the live Zoom that we have just in a couple of minutes. So goodbye and always take care.